Hi, now an example for estimation in logistic regression. So suppose that there is one numeric predictor x to regress binary y, and we have the scatter plot as this. So we have 100 observations, and actually the 50 observations with y is equal to 0, and 50 observations with y is equal to 1. So now basically we want to calculate the probability of y is equal to 1 given x. So you can see, for example, that if y is around here, x is always 0. So success probability is, okay, may not be 0, but very close to 0. So maybe around here. But if x value is really large, maybe around here, the most likely the y is equal to 1. Maybe one exceptional case here, but the other y values are always 1 if x is larger or equal to 1. So probably the success probability is really close to 1. So in the middle, we have maybe the more non-trivial thing. Here, probably success probability is only 20%, maybe. And around here, maybe probability is 80%. So around here, maybe 20%, around here, 80% or something. So we want to estimate this kind of curve. So this is the F inverse of x beta, or F inverse of the beta naught plus beta 1 x. So in this case, probably the beta 1 is positive. So larger x means the larger probability of success. So that is our objective. And how to fit in R. The R has many functions, statistical estimation function, and we use this GLM function. And if we specify just the y on x, this is the same as the linear model LM function, then specify the binomial parenthesis logit, then we can do a logistic regression. Also, we can choose the probit or some other techniques. And then the summary of the GLM1, so this object, then we can get estimate. So negative 0.64 is an intercept, and 1.27 is the coefficient of x. So that means basically the F inverse of x beta is F inverse of negative 0.64 plus 1.27 times x. So that means this probability. So this is the probability of y is equal to 1. So this is represented by e to the power negative 0.64 plus 1.27x over 1 plus e to the power negative 0.64 plus 1.27x. So this is the result. And how reliable these estimates are, then these are standard deviation. So only 100 observations, but it's reasonably good. For example, the coefficient of x has the z value of 4.48. So this is basically the signal to noise ratio. So 1.27 divided by 0.2867. So this is 4.438. And for logistic regression, actually this does not follow. We don't really know what distribution this value follows, but actually this is MLE. So the maximum likelihood estimator follows a normal distribution if sample size is large enough. So we rely on that the asymptotic theory in statistics, and we use the normal distribution to calculate this p-value. So basically this is the probability of the z absolute value is larger than 4.438, and here z is normal 0.1. Then you can see this is highly significant. And we have several the important values, the deviance and degrees of freedom and so on. I will explain it later. So, and this is numeric approximation, the optimization procedure, and it run some iteration method 4 times to reach this solution. Yeah, so this is just explanation what I provided. So yeah, at least we can say that the beta 1 is significantly different from 0, and beta 0 is also significantly different from 0 because the p-value is 0.0185, which is less than 0.05. Okay, so I said that the optimization is done by maximum likelihood. So if we define likelihood function and we numerically optimize it, then we will get the same answer. So here is the code. So this is exponential of x over 1 plus exponential of x. So this is the f inverse of x. So if we put the x beta inside the f inverse, then we take summation, then we can calculate the likelihood function. So yeah, you can see that this part is the 1 minus f inverse of x beta. So that is the beta naught plus beta 1 times x. So here beta naught is b of 1 and the beta 1 is b of 2. Then actually the first 50 observations are failure. So we calculate the 1 minus this and take summation. And success case, that we just use the f inverse of x beta as the likelihood. So this is f inverse of x beta. So this is the success, the failure. This is failure, and the last 50 observations are success. So yeah, and we take summation for both and take summation. But we define the minimum log likelihood because optimum function in R, the minimize function. So not maximized function. So we want to maximize likelihood. So we define the negative log likelihood. So we want to minimize the negative log likelihood. So here, to define the function, the negative of log likelihood function, the technique is that we should have only one input, b. But to make b as a vector, then we use the b of 1 and b of 2. Yeah, so this is necessary, coding, if you want to use the optimum function. And optimum function works in this way. So the first argument is initial value. So just any value, maybe you can start with 0, 0, or if you have a good guess, then you can put the initial guess in this case. So negative 0.2 and 0.5 is just random number. So yeah, I was born on February 5th, so just I use 2 and 5. Okay, so the minimum minus log likelihood. This is function to minimize. So this is a function whose input is the 2-dimensional vector b. So the initial value should be also 2-dimensional vector. Then we get parameter here. So the first component is the b beta naught. Second one beta 1. So this is estimates. And these are exactly the same as the previous page. Yeah, slightly different, but this is just the approximation error.